আমি স্যারকে জব করেছিলাম, ভিডিও দেখলাম, তারপরে স্যার
ও স্যারকে তারা তো একই। তারপরে কি বলতো কি স্যারের ওই লগইন চলে আসছে, মানে ওটাই তোমার অলগদা।
হ্যাঁ
ওই প্রথমে যেরকম করলে হয় না, আবার লগইন মানে স্যার ওই ইমেল অ্যাড্রেস চাইছে স্যার, ওটা হবে না, আবার নতুন করে লিঙ্কটা খুললে তাহলেই আসে।
হ্যাঁ হ্যাঁ হ্যাঁ।
আচ্ছা অলোক বাবু,
হ্যাঁ বলুন।
স্যারকে কি আপনি ফোন করবেন, নাম্বারটা বলবো?
স্যার আপনি করে দিন না, করতে মানে ঢুকে যাবেন। স্যারকে আমি দেখেছিলাম তো একবার। হ্যাঁ
আচ্ছা আচ্ছা।
তুমি স্যারকে আরেকবার লগইন করতে,
হ্যাঁ
ওই লিঙ্কটা ব্রাউজারে ওপেন করতে বলো, তারপরে প্রবলেম হলে আছে ফোন করুন।
ট্যাব গুলো বন্ধ করে আবার চালাতে বলুন,
সব ট্যাব গুলো
আচ্ছা,
বন্ধ করে। তা নাহলে তুমি আমাকে দেবে, আসেই তো আমি ফোন করবো। তুমি একবার বলো স্যারকে ওইটা।
দিলীপ তুমি কথা বলো না।
তুমি স্যারকে ওইটা বলে দাও, তারপর আমি বলেছি।
আচ্ছা আচ্ছা দাঁড়া। গুড মর্নিং স্যার।
গুড মর্নিং আশিস স্যার, আছে ঠিকঠাক?
ভালো আছি স্যার।
ওকে, অডিও ঠিক আসছে তো?
হ্যাঁ ঠিক আসছে আপনার স্যার।
ওকে ওকে, মিউট করে দিচ্ছি।
Good morning, sir.
Yeah, good morning, Professor
Yes.
Mitra. I think there was some technical glitch. I don't know why it happened.
Good morning, sir.
Am I
We can
audible?
hear you nice and proper.
Yes, sir. Yes,
Yeah.
sir.
Okay.
You are nicely audible, sir. Welcome, sir.
Okay. Thank you. Thank you. So can we
Tanushree
start?
ma'am. So madam will be start. Tanushree ma'am.
Good morning, sir.
Madam, you can start now.
So we have come to day 2 session, and this session will be taken by Professor Rupinder Singh. He's from National Institute of Technical Teachers Training and Research, Chandigarh, India. He will be talking on smart materials for 4D printing. Professor Rupinder Singh received his PhD degree in mechanical engineering in 2006 from TIET Patiala, Masters of Technology, that is Production Engineering, in 2001, and Bachelors of Technology, that is also in Production Engineering, in 1999 from Punjab Technical University. He is Chartered Engineer by Institution of Engineers, India, and UGC Research Awardee. Currently, he is professor at the Department of Mechanical Engineering, National Institute of Technical Teachers Training and Research, Chandigarh, India. He has more than 20 years of teaching and research experience in production and industrial engineering, with special emphasis in additive manufacturing, non-conventional machining and casting. He has guided large number of PhD and master students, as well as coordinated 17 finance research projects. He has received several scientific awards. He has worked as evaluator of projects for international research agencies, as well as examiner of PhD thesis for more Indian university. He is the guest editor for several international journals, book editor, and advisor for many international conferences. In addition, he has also published as author and co-author more than 20 monographs, 80 book chapters, and 550 articles in journals and conferences. Now, I will request sir to please take over the session.
Thank you, Professor, for giving me an opportunity and introducing about the course. First of all, I am really thankful to the organizers, Professor Mitra, authorities of the institute, for this nice work in the area of advanced materials and engineering. I hope in next 1 hour I will be giving some information maybe that may be useful for some of the participants in this area. So the discussion in the area of advanced material from my side will be specifically for the 3D and 4D printing applications. So with the permission of the chair, let us start the presentation. I'm going to share my screen. Okay. Yeah. Can you see my PPT?
Yes, sir. Yes, sir. Absolutely.
Okay, so this is audible and visible also, right?
Yeah.
Okay. So, dear friends, the discussion for this course on advanced materials and engineering, I will be talking about the concept of the smart materials, and specifically we are interested in 4D printing applications. Before starting my presentation, let me tell you why we are interested in this. You see, in our country, the GDP of the country, if we see, the contribution of the manufacturing sector is very less, it is considered to be less than 15%, whereas the other developed countries and of course our comparison we normally say with China, they are contributing around 34% from the manufacturing sector. Whereas in our country, this contribution is less. From last, if you see so many years, it is less than 15%. So the Planning Commission of India, which is nowadays called Niti Yog, they have put a target to, increase this contribution by 10% by 2025. And if you see the website of the Planning Commission, you will see that they are interested in, having more contribution of the manufacturing sector. Now, if you see you are interested in increasing the contribution of the manufacturing sector, one of the important thing is you must come up with some product first. You have to launch it first, and then only you can take the lion's share in the market. Of course, you can think of mass production. You can think of quality products. Of course, those are required, but you see the company or the brand which is most popular is those who have first launched the product. So we have to be really innovative. We have to make the product first, and then we can be really contributing for getting the lion's share in the market. So just a title slide I want to share with you. This is as per the Thomson Reuters data. If you see in our country, India is contributing presently in the range of 5% from the engineering research point of view at the national level, at the international level. Whereas the other countries like China, Korea, Taiwan, so they are much ahead of us. So as a technocrat, the decision we have to take, like we have to innovate, we have to come up with new products so that we can really contribute in increasing the GDP of the country. So one of the area is in the advanced materials and advanced manufacturing techniques. And out of those different processing techniques, one of the way that we are going to discuss is the 3D printing, which will help me in getting a 4D printed properties of the material. So this is just the overview of the rapid prototyping or 3D printing. But we can say this I have taken from the Chang and Chua paper 2005 Journal of Advanced Manufacturing. What it says that if I am interested in developing some prototypes, of course I am interested in functional prototypes, not the non-functional prototypes. It can be through additive manufacturing, it can be through subtractive manufacturing, and it can be through combination of additive and subtractive. And there are a number of techniques available, which may be liquid based, which may be powder based, which may be sheet based, right? And then there are n number of technologies which are commercially available to have this output, right? Again, the idea here is not to describe a particular technology, but to make it customizable, make it low cost, make it as per the tailor-made customized requirement in our country, right? Then only we can think of having a low cost technology and can compete with the Western world. So here we start with this basic introduction. Let us, for some of the beginners, what is the 3D printing or the rapid prototyping? So this is basically a fabrication method where we are interested in making some physical objects that are constructed by depositing some material layer by layer through a computer control. Now, if you see for a layman, this 3D printing is just like a photocopier machine. I have some data in the form of CAD file. That CAD data I am feeding to this setup, which I am calling as a 3D printer, and I am getting a physical object. Now, this is quite common, and people are working on different technologies of the 3D printing since 1980 in a commercial mode, right? And of course, the development was even again 20 years back from 80, maybe in something around 60, 67. People come up with the concept of this 3D printing, right? if you simply see the development of this particular technology, so this was developed using a inkjet printer, and people started using a nozzle of the printer, and in place of one nozzle they put two nozzles, and from one nozzle some ink was being sprinkled in the form of powder, and then from the second nozzle some binder was being sprinkled, then the layer of powder, layer of binder, again layer of powder, layer of binder, so we are getting a thickness in the z axis, right? So this was how the 3D printing actually started, right? And based upon the requirement, powder based, sheet based, polymer based, then of course nowadays we are very much using the metal based 3D printing in a big way, right? And it is expected that in coming 10 years we may see that the whole subtractive manufacturing is shifted to additive manufacturing in a big way. I'm not saying the everything is going to change, but of course both the technologies will go hand in hand, right? So here now the idea is, if I can add some value to my functional prototype with the use of 3D printing tool, because this tool is basically giving me a flexibility. So this discussion that we are going to make in next 1 hour, we will be seeing some of the example how I can make my printable material really smart, and how I can customize some of the properties for some useful application. So again, starting from the base, so I have some CAD file. That CAD file may be IGS file, maybe STL file. Nowadays, directly CAD file from any commercial software package, maybe CATIA, ProE, Unigraphics, you can take and can print a 3D part. So you have something, the position of the materials layer by layer, and then of course in a physical space you can think of making those products. So this is the another diagrammatic representation. So I'm making the part layer by layer, and finally some 3D printed component is available. So what is said that each successive layer is bonded to the preceding layer, which may be melted or partially melted, or sometimes you may think of glue sort of operation on the some build platform till you got a final 3D printed part. So this is a very established technology, and a lot of people have reported different commercial. You see, more than 30 such type of established 3D printing technologies are available, right? Now we are interested in adding some special feature to this 3D printed part. Is it audible to all? Am I audible, please?
Yes,
Is
sir.
it audible?
Yes, sir.
Okay, great. Okay, so in 4D printing, what we are saying is that 4D printing is an extension of the 3D printing. Basically, I am interested in printing of a smart material, or I am interested in adding smartness to the 3D printing.
Yes, sir.
Right? Okay. So if I am interested in printing something which can some printed part is there, and I give some stimulus to that part, and it behaves in a controlled manner, I will call that some sense has been added into this material. Let us understand this with a simple example. Suppose I take a piezoelectric crystal and I apply load over that crystal. So there is a change in dimension. Now you release the load, again it will come back to the original dimension. Now we can do this exercise number of times. That means you can put a load and then release a load, so the dimension will be changed in a controlled manner. So because of this property of a crystal, piezoelectric crystal, we are using this in a typical transducer applications, right? Now just imagine I am in a field, and I saw a sunflower, and that sunflower always faces towards the sun. So there is a actual movement of the flower in a way that it is always moving in a way that Earth is moving around the sun, and it always have some sort of angular displacement. Now that means there is some stimulus which is basically a light which is actuating some mechanism in that particular physical object. Now I am interested in finding some of the stimulus that can help me in a way that it actuates actually, maybe in the form of some displacement controlled way, maybe in form of some change in color, maybe in form of some smell, like that way. So I call it as that material has got some sense. Like we have the concept of photopolymers, which are activated by some spectrum of light in a particular range, right? So they behave in a controlled way. So if my material is in a way it is responding to some stimulus which may be controlling its feature, right, as a function of time, we call it as a 4D material. Now suppose that material is uh, taking the effect of more than one stimulus, and I can control more than one property, right? Then it can add one more dimension into it. Like for humans, we normally see, uh, we say that we can see, we can smell, we can hear, we can feel the touch, right? So similar, so these senses are given to us by the God Almighty. So similarly, we can think of adding some more senses to the material, right? And that means we are adding more dimensions to the material. People nowadays have even talked about the ninth dimension, means different stimulus. The material is being actuated by different stimulus, and that is basically contributing to a particular property. All of you may have visited some of the these malls and all. There they have some simulating place where they will say that this is a 9D experience you can see, right? So like in a 3D movie, you add some features like feeling of touch, feeling of smell, and then you can have some feeling of rain, some sound, that way. So you are adding more senses to the material. Similarly, here in 4D printing, I am interested in adding more sense to the material. So that sense is basically added by some stimulus. So that stimulus may be in the form of light. That stimulus may be in the form of some electric current. That stimulus may be in the form of some magnetic field. It may be in the form of some chemical reaction. It may be some hydro effect. It may be some hydrothermal effect. There can be more than two stimulus. So even if you see some of the papers in this area, people have talked about 9D properties of the material, right? So here we are just concentrating on the 4D property, because this also add a lot of value. Specifically, once I am interested in developing some smart sensors for some typical applications, and then of course some self-assembly features of some different type of material. I will discuss some of the case studies with you, right? So what can be the reason of this smart behavior? It can be some intrinsic property of the material. It may be some extrinsic property of the material. Like intrinsic property, it may be like property like self-expansion, self-contraction. I have given you the example of that the piezoelectric crystal, just applying a load. So this is a physical, mechanical load you are applying, and then there is a change in dimension. So that actually thing we can also see for some 4D printed material. One of the example is we may think of using a PVDF based polymer printing, and that PVDF is basically actuated with the electric field. If I apply a 4.5 volt kV, 4.5 kV potential I apply, so there will be changing from alpha phase to beta phase of that particular material. So I can think of some volumetric expansion and change in the dielectric constant and the charge capacity of the material. So this basically is the inherent property of the material. Now then, this may be some properties may be added to it. It may be through reinforcement or through the metamaterial. So this comes under the extrinsic property, which is based upon the external factor. Now taking the same example of the PVDF material, I am interested in some piezo property, right? So I know that PVDF has some piezo property, but now I want to increase this piezo property. So I can do some sort of a reinforcement of material like barium titanate. This will help me to increase the piezo property in that material, right? So we have actually observed this for typical 4D applications. Then the metamaterial concept is quite common. People in specifically the structural engineering application using this metamaterial concept, where the property of the material or the finally, the strength or some other features we are getting into the some functional part is not because of the inherent property of the material, but it is dependent upon the angle and links at which that particular material is fabricated. It may be through printing or some other conventional process, right? To understand this in a simple way, let us take the example of the trusses. In a typical railway bridge, we use the concept of trusses. So basically it helps to reduce the weight of that section, but the angle and the links that are being used in the trusses, those are really important. So we can use the similar concept and can print some 3D printable material, right? And we can see there are some smart features in that material, so that result to the metamaterial concept. Typically for the structural engineering application, people are using kirigami and origami structure to prove this concept. Okay, so there can, once we use some sort of a stimulus, we can also program it. So we call it as a one-way programming, two-way programming, and multi-stage programming. So what is one-way programming? Suppose my material is in state A, I give some stimulus to this, it is converting to the state B, right? Now I give again stimulus, it will come back to the state A, right? So this can be the one-way programming. Then in two-way programming, it can be like I'm using some electric current. You just switch on the current, it goes to the state B. You switch off the current, it comes to the state A. So this is a two-way programming. So similarly, there can be a multi-stage programming, like you can have a different stimulus from A to A1, then A1 to A2, and you can think of multi-stages, and those stimulus are helping me to get some desired property of my functional prototype, right? So let us now see with the help of some case studies. First, one or two, I will talk about the basic about the 3D printing as a case study, and then we will see how we can add some 4D property to this 3D printed material. So this is the that I am trying to discuss with you. This is one of the very common low cost, very cheapest technology, and I suppose this is available nowadays in every engineering college, diploma college across the country. So what this technology is, this is called fused deposition modeling. Here what we are doing is we are having a spool of material. This is basically a polymer. So this polymer spool is being forced to a liquefier head through some gear drive mechanisms. You can see here are some drive wheels, right? So I am forcing this feedstock filament, which is of the polymer, and I am forcing this polymer to enter into some liquefier chamber. So here basically on the inner side of this liquefier, we have a heating arrangement, and once I force my polymer to enter into this liquefier chamber, then on the other side I have a some of the nozzles where some reduced dia of the wire is coming out. So the inside, once I at the inlet I put the material, the dia of the wire is 1.75. So once it comes out, this becomes normally 0.8, right? And for a different commercial based printer, you can think of the wide range of diameter of the wires. Normally for the commercial printer, this is in the range of 0.5 to something around 2.5, but most commonly used size is 1.75. And of course you can change this nozzle dia also, and you can think of the wide range of this nozzle dia, right? And finally we can print the material layer by layer, and we will get certainly the some thickness of the component, right? Now to prepare this feedstock filament is quite interesting. People are using extrusion based techniques, typical single screw or twin screw extrusion they are using. But now just imagine if I add some additional property while extrusion to this material through reinforcement. I can think of printing a smart material. So here you can see typical layer by layer some material has been printed. So whatever the wire is coming out of the nozzle, that is being deposited layer by layer over this platform. So as the part is being printed, so the platform is being loaded and people are making it a 3D part. So here some of you may have a question, why we have a two wire spools over here of two different colors. So basically one wire spool is of a build material and another is of a sport material. Build material is basically a oil soluble material, and sport material is basically a water soluble material, right? So once we, let us say I am interested in some complex part, once I have a cantilever type situation where some, I have to sport some part, so I build that part with a sport material, and finally once the part is ready, I just put it in water, make some basic solution, and the water soluble part is basically getting dissolved into it, so I get a final finished component. So that is the basic technology, and that has been developed, you see, in early 80s. Now we are interested to add some special features to it. So let us understand how. Now this is the first case study that I'm going to discuss with you. Here what we are done is we are using a PLA as a composite matrix that has been reinforced with hydroxyapatite and tryptosin to make some biocompatible and biodegradable feedstock filament using twin screw extrusion, typically for the 4D applications. Now you see, this is a special situation where I am interested in developing some spacer for some biomedical application. Just imagine there is a patient and some bone part is there. You may know that this bone is having a feature that it can grow. Suppose there is some trauma patient, there is some accident, right, and some there is some loss in bone part, but that is actually having a capability to self grow. In humans, normally, if we have a case when some bone part is missing because of some accident, right? So it may grow in maximum up to 6 months to 10 months. But if we take these typical case, in case of the animals, specifically for the veterinary patient, it may take just 10 to 12 days. So naturally the growth rate is really fast. So but suppose there is some loss of the part is there, and I'm interested in supporting that patient with some spacers. Suppose there is like you see the bone is like this, and because of the accident and some short of part is there, right? So as a typical mechanical engineer, I am interested in providing some spacer. So that spacer must be there for a period till the full bone growth is not there, right? So once the bone growth is there, that spacer I have to remove, right? So that is the requirement, right? So for this purpose, we are using a PLA as a matrix, because PLA is basically a biocompatible and of course biodegradable. So we are interested in finding a situation at which the rate at which my bone is growing, at the same rate my spacer that I am putting mechanical in between, it must dissolve. So since the PLA can dissolve, I can use that as a spacer. Now, another important thing in this is once I am using this spacer of a PLA, which is of course biocompatible and biodegradable, I can control its density. I can make it part really hollow from inside, so that the degradable rate can be really controlled. So as you know, in 3D printing, I can control infill pattern, I can control infill density, right? So that is really a good, giving me a good control, specifically if I am interested in typical biomedical application. Now this hydroxyapatite, which is basically a calcium-based mineral, that is basically helping in the fast growth of the bones. It helps to grow the osteoblast cell. So normal, the literature says if we put 8 to 10% of the hydroxyapatite, this is again helping me in a big way to growth of the bones, right? And tryptosin is again a waste that is available from the fish bone powder, right? A report says that if I put 1 to 2% of the tryptosin, it helps in a big way for the growth of the osteoblast cell. So this case study is helping me to develop basically a self-growing type bone, and I am putting a spacer in between, which will dissolve at the same rate at which my bone is growing, right? So what we did is we use a typical twin screw extruder for this extrusion process. You can see this is the view of the twin screw extruder. I have a intermeshing screws over here. I can put some different quantity of the load. I can put a different RPM. I can change the torque. I can change the temperature, and I can change the composition. So you can see here some feedstock filament through extrusion is coming out. So and I'm collecting this this filament over this spool. So in this particular picture, you can see 91% by weight PLA, 8% by weight hydroxyapatite, and 1% by weight tungsten that has been extruded. And now this will be fed to the filament that I have just shown you in a previous description of the FDM process, and I can print this this component for making some really useful part. This is again an important thing to understand. We try to perform the thermal stability analysis of this particular material. You can see along the x-axis, I am changing the temperature and the time, like from room temperature to some high temperature, maybe around 150. Then again, I'm cooling from 150 to room temperature, then from room temperature to 150. And so I am trying to see the energy absorbed in different heating cooling cycles. So I'm interested in the crystallinity of the material. I am interested in the glass transition temperature. I am interested in the melting temperature of this material. Like for example, to understand in a simple way, suppose I have purchased two polymer based buckets, and one bucket I put it in my bathroom and second on the rooftop. So just after a few days you will observe that the material, that the bucket, polymer bucket that I put in the rooftop, which was under the aggressive harsh environment, means heating cooling cycle was different as compared to which was put inside the controlled environment. There is a wide deformation that has been reported specifically once the material is under the aggressive environment. So what we want to do with this type of study is, like, I am using some particular implant or some particular material in a particular environmental conditions, like it may be orthopedic, it may be dental. What will be the range of the temperature condition over which it will be working? So that we should understand whether this material that I have developed is going to be thermally stable or not. So keeping all these things, we try to understand for the different composition whether this will be thermally stable, right? And then we did finally the microstructural analysis, which is based upon the SEM based optical photomicrographs. You can see in this picture specifically, I got a open porous and the fibrous structures, which was really useful for the growth of the osteoblast cell. Like just again example, from one side of the bone is there is another side of the bone, in between you have a spacer. Now the osteoblast cells are growing, and you see because of the open porous and fibrous structure, the blast cell of osteoblast cell will be basically resulting into the interwoven structure. And finally you are controlling the dissolving rate of the PLA, and you are using the HAP and tungsten to increase the growth exponentially for the osteoblast cell. So we basically expect a better recovery for such type of the veterinary patient or for humans also. So this is the way where we can print some 3D part, 3D printed, which is a functional part, right? And this is getting consumed in a controlled way as a function of time, and it is helping to grow the bones in a natural way, and the comfort level to the patient is much more as compared to any other conventional way of supporting those type of the broken bones like that way. So this is the one case study that I want to share with you. Here is the another example. In this particular case, what we did is we use a ABS and polyamide, and we reinforced this ABS and polyamide with the banana fibers, right? So this is basically helping me to waste management in a big way. Like in the different part of the country, we have different type of the agriculture waste, and the disposal is really creating so many environmental issues, like by burning of the paddy straw and these type of the things. So once we were in the development of the feedstock filament at our end, so one of our supplier was from Jalgaon, And what he told us that at that place there is a lot of banana production, and the banana fibers are available at very less cost. So we try to reinforce those banana fibers in ABS and PS6, and we got a really wonderful result for the 3D printed parts. For this particular case, what we did is we used the banana fibers of 1000 micron and dia 100 microns. There is a very good paper by Banerjee et al., where the authors have basically reported how to condition these type of the banana fiber for different type of the reinforcement. So what we did is to start with, we selected the 5% reinforcement of the banana fiber in different polymer metrics like ABS and PS6, and we try to print some of the functional part. Again, you see over here is again the same twin screw extruder, then the 3D printing, and this is the printing of the tensile coupons as per ASTM D638. Similarly, we try to explore the flexural coupons using ASTM D790, and similarly for the compressive parts also. So for processing of the feedstock filament, some standard operating conditions like temperature, nozzle dia, torque, this we can control, and depending on the different type of the reinforcement, I have to do some DOE to manage these type of the input parameters for some typical mechanical properties. Again, here you see we did the thermal analysis, and again from room temperature to 250, then from 250 to room temperature, we try to see how this material is behaving. So what we observed that in repeated cycle with the reinforcement of the banana fiber, the heat capacity was improved. Even the melting temperature was improved, which has been observed for both for the ABS and as well as the polymer, which is basically a nylon 6 based polymer matrix composite. Similarly, the improvement in load, tensile strength, percentage elongation, and of course the controlled porosity, these type of observations were taken. So why I am showing this is, if I am interested in, now you just see, I'm interested in making some roof, right? And for making a roof, I need to put some iron bars, and those iron bars are tied with the MS wires, right? So those MS wires basically those are susceptible to basically corrosion once they are in the exposure of uh, different oxygen and water content is there, right? So we can think of tiding those bars using these type of the polymer wires, right? And we can use it for fairly good period of time, because there will be no problem as regard to the corrosion is concerned, and this is much cheaper than those, right? And the second advantage that I am getting is, here in this case the percentage elongation is 13 to 14 times more than those of the MS wire that I am using. So in case there is a chance, because of the movement in the earth, some wall is going to collapse, so it will give you more percentage elongation, so it will not going to collapse in a movement, rather it will have a more elongation, right? So that is the advantage we are getting. Now the 3D printing point over here is, I am able to prepare some feedstock filament of a 3D printer from the waste. So this is going to help me in a big way as regard to the waste management of these type of the material is concerned, right? Now let us see how we add some property as a 4D property to this material. This was the 3D printed part, now the 4D part. So basically I have to give some stimulus to some material, and with that stimulus the material is going to behave in a controlled manner. So with the stimulus I can add on some property, I can switch the mode of the material, and then I can do the reverse also, and I can do in steps also. So the stimulus can be in the form of some electric field, it can be in the form of load, it can be in the form of light, it can be in the form of magnetic field, some chemical energy, or some thermal energy is there. Now let us see one typical example. This is the case study that we have performed with one of our collaborator in Italy, Professor Fernando, and we are interested in developing a particular sort of a cabin for some place in Canada and US, where the temperature outside is -30, and we are basically interested in replacement of the wooden structure because of the depletion of the natural resources. We are no more interested in cutting more woods, so we are interested in having some situation where we can replace the wooden structure. Number one. Number two, we are interested in some self-assembly applications. We are interested in making some tiles. Number three, we are interested in some recycling of the polymers. Right. So keeping these three things in mind, we try to develop this case study. So the first setup that you are seeing over here, this is the melt flow indexer. This is basically required to understand what is the flow property of the materials while I am making some polymer based 4D materials. All right. What actually we do is we have a the polymer that we put it in some barrel. I fix some temperature. I apply some load. Then at a particular load, once the material at a particular temperature, the material is forced to move through this barrel. On the other side, we have a small opening, right? So how much gram of material in 10 minutes is coming, that is called basically the MFI of the material. This is basically the one of the basic rheological property measured in gram per 10 minutes, and that is required for basically running my material or of a composite or a virgin polymer on a 3D printer, right? So this is the first test. This is as per ASTM D1238 standard, right? So this is the first thing we have to ensure. Then once I have ensured the particular composition, then I have to prepare the feedstock filament for the batch production or the mass production. So I have intermeshing screws. So I'm putting some material over here, right? Then these screws force the material through the die. So I have a feedstock filament. Now that feedstock filament I am feeding to the some liquefier head, and then with some XY movement and Z movement, I'm getting a 3D printed part, right? Now the actual case study. Now you see in our office cabins or even in our residential places, right? We used to go for the PVC paneling. PVC is giving me good strength, but the problem is the biocompatibility. Now once the useful life of that PVC panel is over, like it is not able to give me good color or good luster, then basically we throw it outside. So this adds to the plastic solid waste, right? And of course this is not biocompatible. So what we try to do is we try to procure a PLA which is a biocompatible, right? And we try to reinforce with a PVC which is of course not biocompatible, and then we try to add some wood dust which is a waste from some sawmill in place of the wood, and to add some smart property, to add some self-assembly feature, we add some iron powder into it. So in this case we try to use the Fe3O4 magnetite powder, and we try to print this material layer by layer by preparing a 4 different feedstock filament, and we try to develop some sort of a tiles, right? So those tiles I am interested to 3D print and use in a cabin for self-assembly application. So in this particular picture you are seeing the granules of PLA. Here are some PVC, then some magnetite powder and some wood dust that has been used. So reason I have already explained. The PLA because of the biocompatibility, PVC to address the waste, Fe3O4 for the magnetic properties, wood dust basically as a good thermal insulating property. So we try to observe the different composition, and then we try to work on different torque available on the extruder, then their temperature, then the load condition, and we use a DOA, and we try to prepare the different feedstock filament. Then we did a basically VSM, vibration spectrum magnetometry test, to understand whether my material is really having a good magnetic property. Just imagine what I am trying to do is I am trying to print a let us say a rectangular tile, right? Just imagine I have a metal frame. In that metal frame, which is of course in the form of a wire mesh, right? So on that wire mesh, once I give a current, of course less than 12 volt to this, right? So some electric field will be there. Because of that, there will be some magnetic field. Because of the magnetic field, it will be having a the attraction. So for that attraction, what I am trying to do is I am trying to print a sort of a layer by layer tiles with the lower layer, which will be attached to the wall, that will be having a high composition of the Fe3O4. Then the next layer with a, let us say, the more composition of the wood. Then the next layer with the composition of PVC, and the top with a PLA. Right, so we try to measure with the VSM. We try to develop the BH curves, and we try to measure the magnetization, corrosivity, and retentivity of the material, whether this material can really stick once we apply a magnetic field. So this will help me in typical 4D property of the self-assembly applications, and we were able to get with the different composition of the Fe3O4 the required magnetization, corrosivity, and retentivity. Means even if I switch off the magnetic field, for how much magnetic behavior that material will be performing, how much magnetic field it will be having. So these type of the basic observation we did for the selected composition of the material, and then we did some ANOVA analysis, like a typical statistical tool to understand which parameter is more contributing for a particular property. Then some SEM and EDS analysis was done. You see from here, I have a PLA, so repeated experimentations were performed for finding their melt flow index. Then for PVC, then with the different reinforcement of PLA into PVC, like 10%, 15%, 20%, 25%. So what will be the effect of two type of reinforcement? Then what will be the effect of the multi blend of the melt flow index of the material? Similarly, for the reinforcement of Fe3O4, similarly with the reinforcement of wood, we try to see what is the effect. We also try to observe with these type of reinforcement, what will be the peak load, what will be the peak elongation, break load, break elongation, peak strength, break strength, percentage elongation at peak, percentage elongation at break, then young modulus, then of course the modulus of toughness also. Like we try to see the area under the curve, then their surface hardness in form of Shorty property, again their thermal stability, and different BH curves for different type of the materials. So what we observed is we were really able to develop multi blend these type of the material with respective magnetic, thermal, then mechanical properties. And of course this can be really printable, and those printable sort of a tiles, those are once actuated through a magnetic field, they show the self-assembly feature. So this is one of the simple way I can make my 3D printed part a smart, and it can behave as a 4D material. Right, so similar to this, we try to reinforce different type of material into the polymer matrix. Like in this particular case, we reinforced graphene into ABS, and what we observed, once we put the different composition of the graphene into ABS, we try to see their rheological property in terms of MFI, then their thermal stability analysis, how they are behaving, like with the different reinforcement, what is the effect on their heat capacity. You can see with the reinforcement of the graphene, the heat capacity is basically increasing. And then of course we try to see the effect on their magnetic property in form of corrosivity, retentivity, and magnetization. Right, so both in positive and negative, basically changing the field of the magnetic field, we are trying to see this. And based upon this, we observed that of course any polymer with these type of the reinforcement can be made as a 4D printable material. Now this is the another case study where we try to put the barium titanate in PVDF for typical 4D applications. So as per the literature, it says that the graphene, if we reinforce up to 2% in PVDF, this is giving the good results. So then with this proportion, different BTO, barium titanate, was reinforced, and we try to prepare the wire, and then we try to see their peak strength, break strength, their modulus of toughness, their stress strain curve, then their thermal stability, and we try to see their D33. We were able to get a 20 picocoulomb per Newton as a piezoelectric effect, right? So this can really help me in developing some transducer type application. So this is again a way from where with the from the waste I can actually make a useful product, right? So this is the another case study for making some 4D printable properties of the material. In this particular case, we have put the ZNO nanoparticles into the PLA, and we try to tune the thermal, mechanical, morphological, and the shape memory properties. Now if you see the stepwise over here, I have some thermoplastic granules which were of the PLA, and ZNO nanoparticles were just reinforced into it. So prepared the feedstock filament. So that feedstock filament was processed for different thermal properties. So I can see what is the thermal property without reinforcement, then with the different level of reinforcement, 1%, 2%, 5%, what is the going to be effect on the thermal stability, whether the thermal stability is improving, so we can check it. So one important thing we did over here, we make some U-shape component, and then we try to see the effect of the the stimulus as water and the temperature. So what we observed, once we made this type of view, and then I put it in water for 5 hours at the temperature of 25 degrees Celsius, and then after 5 hours we removed it and we try to see what is the recovery. So what we observed with the 1% ZNO, the recovery was 97%, means the U becomes V, and once you put it for some period, then it again regain its position, right? So what we observed is there was a effect of the temperature. So at different temperature, this behaves in a different manner. Like at 40 degree, this was behaving in a different manner. Then we try to see this material behavior at certainly very low temperature, and then at the glass transition temperature. And what we observed that 99.9% recovery is also possible. So this can be really helpful for me as a 4D material for some typical sensor applications, right? So we try to correlate why this material is behaving like this. So that has been correlated with the porosity percentage, and we observed that the porosity was much controlled at those particular situations, right? Now I am giving some examples, 1 or 2 examples to develop some own smart materials using a simple physics principle. Like for example, I'm making some 3D printing. So this is you can see this blue color is basically a non-conducting layer. This is a conducting layer. This is non-conducting layer. This is a conducting layer, and this is again non-conducting layer. So what I'm trying to do is, on the conducting layer, I am making some electricity to move. Suppose the electricity flow is in this direction, so there will be north, there will be south. Then in the second layer again there will be north and there will be south. So this south and north, there will be attraction, so the part will have a compression, right? So if there will be a south, if just I change the direction of the current, there will be a repulsion. So basically, using basic principle of physics, and just by changing the direction of the current, I can make some 3D printed material as really smart for some some sort of a cavity filling type structure, right? So that actually we try to do. I will show that example. Similarly, we can think of using these type of the smart materials for some hybrid applications. Here basically in USM process we try to hybrid some of the application you see over here. In typical USM we can use the transducer developed with the technology that I have just explained to you over here in place of the present piezoelectric transducer. Then here the tool that we are using in USM for the drilling of this surface, this is normally of the metallic material. What I can do is I can 3D print this, and here you can see I am doing the combination of the broaching as well as the machining, right? What I have done over here is, here this protruded portion which is going to be in the drilling part, this is made by the 3D printing, and here up to this region, this is a rough zone, then semi-finishing zone, and then the super finishing zone that has been 3D printed, right? So once this ultrasonic drilling will be there, so this will be doing the combination of drilling and broaching. So this is basically going to be a hybrid process, right? So that is the possibility with this type of the smart materials. Then one thing more we can do, you see, in typical 3D printing applications, what we observe is, once we have a 3D printing, my nozzle is normally circular in nature. So once there will be a deposition of the material, it leads to the some elliptical part. So some these ellipses are, once they are placed in this way, there is a, of course, one is a staircase effect, another is there is a air gap. Because of this, there is a poor surface finish. What we can do is we can think of some smart material based nozzle. This can be polymer or it can be metal, right? So because of this is basically happening because of the Barrow effect. I can think of having some smart nozzle where, because of the Barrow effect, it can automatically change its profile. Like suppose the profile is like this, it is giving me the output like this. So I am getting a triangular shape layer deposition, and then in the second layer I am just putting the reverse direction of the layer deposition. So here you see there is a very less air space, and the surface finish that we will observe will be much better, right? So this can be really a smart nozzle that we can make, right? So similarly we can think of using a multiple nozzles for the 3D printing, and then one nozzle is giving me output like this, the second nozzle is giving me the output like this. So once there will be assembly, so there will be less air space. So we can think of different type of the application of these type of these smart materials, and can use them for different number of applications. So that's the thing that I want to share with you. Now I'm open for any questions, if anybody wants. Yeah. Do we have any query, please? Yes.
So there are some questions in chat box.
Yeah, please.
One question has been asked by our director, sir, Dr. Prabhas Bose. He have put one question that, sir, can we upgrade an existing 3D printer to 4D printer?
See, there is nothing like a 4D printing. 4D print, there is nothing like a 4D printer. 4D printing is basically the extension of the 3D printing. I have to think of a stimulus that basically help me in getting some 4D properties. Like for example, I say in a simple words, as a human we can see, as a human we can hear, we can taste, we can have a feeling of touch, we can smell. So these are basically senses that God Almighty has given to us. So similarly, if I add some sense to my 3D printed material, as I am adding those senses, more dimensions are being added as a function of time, right? So I have a 3D printed material which is through some 3D printer. Now I give some stimulus to this. So because of that stimulus, that material is activated, and it is giving me some desired controlled output. The stimulus can be electric field, it can be magnetic field, it can be a load, it can be some chemical energy, it can be light, something like that, right? So all 3D printed materials, we need to understand what is the stimulus that will basically help me to getting a 4D property. So all materials of your commercial 3D printer, all are having the same features, just you have to add the stimulus otherwise. So that is the thing, right? I think I have made my point.
Another question is that,
Yeah.
what is the present status of 4D printer? Is it
Yes,
commercially available?
yeah, this is very much related to the previous one only. So there is nothing like 4D printer. It is a 3D printer only. You need to see the stimulus for your material. So what material is going to provide some stimulating effect, and you have to program it actually. So that is the programming part is after the printing, right?
Okay, sir. So another question is there. It's asked by Devaprasad Ghosh. can nanoparticles be printed by 3D printing?
Yes, of course, you can print any nano reinforcement, right? Basically,
I
you
think
know,
metal printing, they use powders. That means nanoparticles are only used.
yes, yes, you can do any, even in polymer printing also. I have just given you the example of putting 1% ZNO, 2% ZNO. Those all were nanoparticles, 10 to 20 nano size. That is very much possible.
So another question is that it is being asked by Hiteshi Tandon. He just have asked to explain what is Barrow's effect.
This is Baru, B-A-R-U. Baru. This is a,
Yes.
okay, this is not Barrow. This is Baru effect. Basically, you see, once we have a, sort of a circular nozzle, right? So because of the, solidification phenomena, once there will be a, layer deposition, it will be not in the form of circle, it will be in the form of ellipse. So there is some contraction in the material, right? So you just imagine I am depositing ellipse over ellipse, right? So there will be air gap. So we want to basically control that air gap. Otherwise, this basically will have a bad effect on my surface finish. So that's why we want to play with the nozzles in such a way. If there is some sort of a contraction like that way, so it must take the exact dimension or near to the dimension. Or I need to do minimum rework to improve the finish. So that is basically we are interested.
So another question is there. It's been asked by Dr. Amalesh Barai. How do you perform 3D printing of banana fibers reinforced composite materials?
Basically, banana fibers we selected of 1000 micron length, 100 micron dia, and we reinforced up to 5% in ABS and polymer using a twin screw extruder. So once we did that, we were able to manage the rheology. Basically, why we use the 5% or any other proportion, that will depend upon the rheology of the material. So basically, we have to do the MFI for that, melt flow index, that is as per ASTM B1238D standard. And normally for the commercial open source 3D printer, what we need to do is we have to manage our rheology in the range of 2.5 to 3.5. So accordingly, we select a particular proportion. Otherwise, I have to change some hardware and software consideration. If I make the reinforcement in such a way that this is between 2.5 to 3.5, so I need not to change the hardware. So that's why we use that 5% proportion. So basically, if you are able to, normally nowadays this is very much possible through the software. You can have a control of the temperature conditions, and you can play with the higher MFI also. So that's why we use that particular proportion.
So another question is there. What is the fourth dimension in 4D printer?
There is nothing like a fourth dimension. Three-dimensional is the part. The fourth dimension, as a function of time, we are adding some controlled property to this. Let us understand in another way. You just imagine there is a baby in the womb of a mother, and we try to see the fetus. Let us say it's in the fetus form through an ultrasound. So we get a 2D image. Then there was a concept of 3D image. Basically, we add volume to that 2D image. Now there is a 4D imaging. 4D imaging is something like I am interested in seeing that 3D printed 3D image as a function of time. So basically, it looks me like a movie moving on for some period of time. So that is a 4D imaging. Now just try to correlate 4D imaging with 4D printer. Now 4D printing is basically a 3D printing part, but I am giving some stimulus to that 3D printed part, and it is behaving as a functional material. Like it can, let us say, expand like a piezoelectric crystal. You release a load, it will just come back to the original position. So that property that has been added to this is basically through some stimulus, right? So that stimulus is changing the fourth dimension, which in particular case can be the length, which in a particular case can be the color, which in particular case can be the angle. So that is basically the idea of the 4D printing, right?
Okay, sir. So what are the limitations in 4D printing?
Of course, the limitation is with the selection of the stimulus and the stimulating conditions. This is really challenging to have a finding the particular stimulus. You cannot use a similar type of stimulus for all the materials. Like some materials may be really having a stimulus as a magnetic field or some hydrothermal effect. So this will be different for all the different type of the materials. So you have to tune it actually. So that leads a lot of experimentation to perform.
So another question is there. It's been asked by Robin Mondal. Sir, it means in 4D printing, we have to look for both the compatibility of stimulus element and the filament materials. But if some kind of new materials is used as filament, then how can you immediately find out the exact stimulus material to improve or control some properties?
I think for this we need to see some fundamental things. As an engineer, we understand that we have some property of the material because of the interatomic arrangement of some atoms, how they are making some bonds, whether they are making some covalent bonds or ionic bond, or there is a metallic bond or the van der Waals forces. So if typically I am interested in finding the effect of the stimulus on some already known material, I can think of using FTIR, Fourier transmission infrared spectroscopy, or photoluminescence spectroscopy to see the type of bonding we are working over, and we can actually predict that this property will be because of this, and we can see their spectrum before printing that particular part. So I can think of controlling specifically their mechanical behavior using this type of spectroscopic analysis. So that is what we can do, and of course we have to use for different type of like SEM EDS based analysis. You can do some AFM based analysis to see how this particular material is going to behave. But of course, if you are developing a new composite, that leads some basic investigations, and of course the study in the material science point of view. That's the thing I can say.
Sir, there are no more questions. So if any query is there, they may mail you. So already the mail has been shared. Thank you, sir, for your information which you gave in 4D printing. I'm also from mechanical department. I also did little bit work, students project work with regarding to 3D printing. But I got an idea about 4D printing today. So thank you, sir, very much. Now we will move for the next session. Our next session will be taken by Dr. Krishnan Bandopadhyay. He is from National Institute of Technology, Durgapur, India, and he will be delivering on the topic study of tensile deformation and nanoindentation of tungsten, nanoparticles for estimating useful mechanical properties using molecular dynamics. Dr. Krishnan Bandopadhyay is a research associate in COE in Advanced Materials, NIT Durgapur, under Government of India, MHRD. He has strong research expertise in a variety of material modeling for structural applications. His research interests include nanomaterials, computational materials science, and multi-scale modeling. He has published articles in several national and international journals. Also filled a patent also. So now I will request Sir to please take over the session.
Okay, but how can I share actually?
A plus sign in the left side.
Oh,
Yellow color.
Sir, beside the webcam button, there is one button.
share option. Yeah,
Yes,
yeah.
yes.
Yes. No.
Yes, we are getting your screen. So now please open your presentation. It will be visible to us.
Is it open? Hello.
We are getting your screen, sir, but we are not getting the PPT.
Visible?
Yes, sir. So please open your Power presentation. Then
Yeah, I have opened it.
No, sir.
No,
After in the application window, from the application window, you have to select the presentation. Actually, whole screen is here.
Okay.
Again, share screen, then application window.
Share your screen.
Then 3 button is there.
Okay.
Whole screen application window.
Now it's coming.
No, sir.
In application window, you select your PPT file.
See?
No, sir.
yes, sir.
Okay,
Yes.
now it is visible. Okay. Then a full screen mode, presentation mode, you just make it.
Okay.
Okay, sir. Fine,
Is
sir.
it fine? Is it fine?
Fine, sir. Okay, you can continue now.
Okay.
Sir.
So, very good morning to all of you, respected faculty member of CEMK and all the others institute, all the participants. And I, first of all, I congratulate to the coordinator and the team member of FDP, online FDP on advanced materials and engineering, sponsored by AICTE. And especially thanks to Dr. Professor Gayan, Professor Das, and Professor Ashish Kumar Mitra for giving me the opportunity to present my work in front of you. So my today's topic is study of tensile deformation and nanoindentation of tungsten nanoparticle. That is basically for estimating useful mechanical properties using molecular dynamics. So that is basically we have developed in using atomistic simulation, as well as I have covered some experimental part also. So this is my presentation outline introduction using through MD modeling and simulation methodology, synthesis and characterization of nanoparticle, tungsten nanoparticle, result discussion, conclusion, and after that acknowledgement. So basically, as we know, tungsten is a very good structural material in critical application and in rocket, missile, satellite, and in many other applications in electrical and also electronics fields also for structural application. Now, to develop nanostructured form of tungsten is a potential candidate for such application and likely to be provide far better performance as compared to the bulk form. For mechanical and materials design of such materials, the deformation and fracture behavior under load are needed to be explored, and mechanical properties are needed to be extracted therefrom. As we know, this is the transition metal. Under transition metal, the tungsten comes. So for transition metal, many application, if we developed as a nano composite, or we are making as a reinforcing material of nanostructured form using some powder metallurgy route or star casting route, so that is very feasible for or potential candidate for many applications, many structural applications. So before experiment, we have to study to overcome the cost of repetitive experiment. We have studied using molecular dynamic simulation. That is very powerful tools, and that is also open source, and molecular modeling and simulation, which is proven to be a powerful theoretical tools. And also we have the configuration file we have, that means the visualization software we have used as a OV2, that is also open source. So anybody, if you're interested for doing molecular modeling using molecular dynamic simulation and OV2, you can download from the open source software or open source from Google. You just type molecular dynamic simulator lamps, and also the OV2, both are available. So before going to the details of molecular dynamics, we have to little bit knowledge on mathematical models. As you know better than me also, somebody knows multi-scale approach, static, dynamic, discrete, continuum, deterministic, and stochastic. So we have only focused on deterministic. So MD is a deterministic technique. So that means no randomness is associated. And stochastic, that means for nanofluids, many people are using stochastic modeling for randomness and for Brownian dynamics simulation. And we have also developed in our lab, that is different multi-scale approaches. So using molecular dynamics as well as finite element method. So both are, one length scale is millimeter and another is nanometer. So nanometer and millimeter scale, we have, when we have developed any composite or any alloy, so we have to develop using multi-scale approach. So we have developed also in our lab multi-scale method. And some views of modeling. A good model, that means modeling is basically imitation of real things. So many greatest scientists are also says something about modeling, but modeling is which represent some object, some phenomena. So as simple as possible. So if the model is simple, so that means you have to capture the important behavior also of any system. So the concept of simulation, as you know, there's a computer simulation because we also deal with big data. So just like when we are doing program using molecular dynamics, then that will take 15 to 20 days also. So processing speed, computational limitation is very much important for molecular dynamics simulation. So we have to check it whether we have performed in i7 processor also, but that will also take more than 10 days for any. So we have to check the limitation, the size of a system. So that is very much important. The number of atom. If number of atom is more than execution of model, the execution of program will take more time. So we have to check. We have to first we have to design a system which is a very specific with a number of atoms within a very limited. So that means you have to doing a program with a very short period of time. So if you're doing in a supercomputer, then that is no problem. But that facility is not available right now. So basic simulation terminology is discrete system, continuous, static, dynamic, deterministic, and stochastic. So deterministic simulation model is one that contains no randomness variables. All variables are known with certainty, no probability is associated with them. And molecular modeling approach is atomistic modeling. So we are doing basically atomistic modeling, and many people doing ab initio first principle calculation using DFT. And goal of materials modeling to predict different properties, particularly when experimental determination is difficult or impossible. To predict how a system is respond when external variables are imposed. Propose a model and simulate also predicts system response. Validation, that is very much important, whether the experimental and your simulation result is valid. Also validation through some literature also. You can do using literature also. Some advantage that is study the materials properties by effect of external variables, well-controlled experiment, prediction capability, and cost effective. So about now comes to the molecular dynamics. The molecular dynamics is basically a computer simulation technique or molecular technique by which one generate the atomic trajectory of a system of n particles by numerical integration of Newton's equation of motion for a specific interatomic potential with certain initial and boundary conditions. So all are together in this definition. So that means specific interatomic potential is needed for doing molecular dynamics, because basically we are assigned some initial position and velocity. And after that, time is not discrete, but we can, to simplify the model, we can discrete the time using within femtosecond or in picosecond. So that means with progressing of time, we can change the atomic position and velocity also, and we track the position and velocity and temperature. That's why we can calculate the molecular dynamics technique. And the MD implementation part, that is very much important. So first of what I have said, that is assigned particle position velocity, initial particle and position and velocity, and specific ensemble. And here we are using NVT ensemble. So ensemble, that is basically a collection of microstate corresponding macrostate. So initial position in initialize the MD implementation part, the specific potential is also important. So basically we are using the EM potential, embedded atomic method potential. So that potential is also collect through some source, that is NIST, that is reliable source, sandia.gov. You also find out some source, some reliable source, but if your potential is wrong, then program is wrong. So otherwise you can develop your own potential using DFT. And after that, force calculation using current position, and integration and updation of position using and velocities after progressing of time. There's a run part. And another, the analysis part is that 6n variable. And first is x, y, z, 3 variables and 3 momentum. So that means total 6. And average the property, and after that the properties calculation, state of matter. So for the initial portion, you have to design the geometry and also the lattice parameter. If lattice parameter is available, it's okay in literature. But if it is not available for nanostructured material, then you have to calculate the lattice parameter. Any properties, whatever you have calculated through the molecular dynamics simulation, that means the nanoscale property. So that nanoscale properties may be different from the bulk property. So you have to check whether this property is correct or not. So then you have to calculate using molecular dynamics simulation, using any type of property, like tensile property, localized deformation property, nanoscale, nanomechanical property using nanoindentation, or tensile property using molecular dynamics, or anything. We have also in last webinar of CMK, I have presented the copper and nickel alloy for some physical properties like lattice parameter and stacking fold energy. That is also very primary property of any material, but whether that value is correct or not, you have to check. If the value is wrong, then your property you will get after any multi-scale modeling, then that is wrong. So you have to calculate the lattice parameter value and the initial assigned value and initial geometry, and that geometry, depend on that geometry, the total number of atom is assigned. So if the number of atom is large, then I have said earlier that the programming time will be more. So we have to check it. And now coming to my tensile model, so that is analogous to the real experiment, that is thermal equilibration. We are using NVT ensemble. So ensemble basically the collection of microstat corresponding to macrostat. And we have using the Nuse-Hoover thermostat, and that is also a well-known thermostat in MD modeling. NVT, that is number of atom, V is volume, and T is temperature. And interatomic potential, that is embedded atomic method potential, and time taken 1 femtosecond, and time integration using velocity valued algorithm. Velocity valued algorithm is by default setting in LAMPS. So LAMPS is using basically the velocity valued algorithm. So no need to change whether time integration is in another leapfrog method or another method. Time integration for LAMPS is by default set by velocity valued algorithm. And by using the scheme of simulation is like testing of UTM, and last portion, that is last 1/6 portion is fixed. Main deformable part is 1/4 middle, and first 1/6 part is a moving part. So using the displacement velocity, you can change the we have changed it 0.121 angstrom per picosecond. You have to change it. If you think that you can change it, and you can see the properties how that if it is dependent on the velocity, displacement velocity or not. So, and another is nanoindentation. That is very method is very earlier. That is 1992 method discovered by Oliver and Farr, and we are using here the rigid indenter. Rigid indenter, the basic the beautiful of rigid indenter is the no interaction between the indenter and the surface. So we have no consider the interaction between the surface and the indent. Only it can indent the surface, and after that, after the localized indentation, we can calculate the property using the Pmax, that is maximum load by area. And area calculation is different for the nanoindentation technique, because in tensile deformation we can calculate the percent elongation, Young modulus, yield strength also. But for a simple indentation, we can predict the material's property like hardness and Young modulus itself. So the nano indentation is very versatile method. So we are using here the single crystal analysis, and also another team of in our lab, they are working on the polycrystal. So the method is very versatile. So we can calculate using rigid indenter, the displacement control nano indentation technique. Maximum penetration allowed is less than the radius of the indenter, and after that we calculate the radius, and after that radius calculation we can calculate from the next slide, that is stage thermal equilibration using Nose over thermostat. First part is the loading part, another is holding, and after that unloading portion. Now from the unloading portion we have calculated the area, we have calculated the hardness, and after getting the hardness in nanoscale, we have calculate Young modulus, that is basically SOAP into root pi by 2 into beta into root A. So, and after before the Young modulus calculation, we have to check the critical height of a surface, that is H max minus epsilon P max by S. That is basically a well-equipped equation designed by Oliver and Farr. So in this way, we can calculate the hardness and the Young modulus from the load displacement plot. So this is the load displacement plot, and we have calculated the hardness and the Young modulus. So quite more than the bulk material, and after that, Young modulus value is basically effective Young modulus value, because that value, if we multiply the Poisson ratio of the indenter, that is rigid indenter, so 1 by infinity equals to 0, so no need to add. So if we add the materials Young modulus, then yeah, the Young modulus quite less. So that means here we present 1170 GPa, 1170 GPa, and it may be reduced. So we can say this Young modulus is a reduced Young modulus. And this is the configuration, initial configuration and intermediate configuration, and after that final configuration after fracture. And this on the tensile modeling. The tensile modeling from the curved test and plot, we have calculated the yield strength, Young modulus, and the percent elongation. And this is the configuration using OB2. The middle portion is indentation, where we can indent actually. Using OB2, we can find out the configuration. And this is the conclusion. Bulk deformation under tensile loading and localized surface deformation have been modeled under the framework of molecular dynamics of tungsten nanocrystal to extract the bulk and surface mechanical property. The estimated value have indicated the dominant role of surface effect of nanoparticle in enhancing the strength and the hardness by several order to magnitude. Now, when we actually design the program, we have to check to nullify the surface effect of the nanomaterial. We are using periodic boundary condition. And another boundary is Singh wrap boundary condition, non-periodic boundary condition is also used. For bulk material, we are choosing periodic boundary condition. That is very much important for initial part of it when you form any program using lamps. The Young modulus value is found to be relatively insensitive to the surface effect of nanoparticle. The present model can be used for the design and development of nanostructured material for advanced structural applications. And this is the references. Last two we are published in 2017 and 18 also. And another part is we have tried in our lab, that is synthesis and characterization of tungsten nanopowder using high energy ball mill. So many people are doing making some chemical route, but we are using the simple method, simply high energy ball mill method. So basically we have to add the copper as a bulk, and we have to reinforce the tungsten nanopowder to enhance the thermal property, because we know the thermal conductivity of tungsten is also high, and melting point is also high. So we have to bulk copper as a matrix can be reinforced with tungsten nanopowder through not only the powder metallurgy route but also in star casting. But in our lab, the star casting route, the main crucible size is large. But we know when we produce any nanoparticle in lab scale, the amount is very less. So if we reinforce 5 gram or 6 gram or 10 gram, so that particle produce nanoparticle uniform size, all the property, the control property, reinforcing. So that is very much difficult. So we are using the pressure compaction, and after that sintered, and we got the material. So it can be presumed that the nanocomposite with combined nanoparticle like tungsten would be highly effective for advanced electronic, first one for the structural, and later on when we synthesize the material for the advanced electronic and electrical device. Now, hence the problem of the design and development of copper-based metal matrix nanocomposite, which tungsten nanoparticle reinforcement has enhanced the physico-mechanical properties, can be taken up as a research problem need for the performance of advanced electronic device. And basically, the XRD pattern of SPPR tungsten nanoparticle, the plane is 110, 200, 211, 220, and 310 for different time. First one is ball mill 11 hour, and we have to optimize the milling time. And that is basically we are taking the powder of tungsten powder that is commercially available. We have taken it from Sigma Aldrich, and after that 16:1 ball ratio using toluene and tungsten carbide ball. We are using the ball milling in our lab, a high energy planary ball mill. And after that ball mill of 13 hour and 20 hour, we got this XRD pattern for SPPR tungsten nanoparticle. And after that also we can calculate the size distribution using DLS, that is dynamic light scattering technique, that is also available in our department under Professor M.M. Ghosh. And tungsten nanopowder ball milling of 13 hour, 11 hour, and 20 hour. We got this size, but that is quite much more. But in 13 hour, particle size range is quite feasible, and mean size is 21. And in the right side top, the 4 vial, that 4 vial contain the nanoparticle we have developed in our lab. And this is basically HT image of SPPR tungsten nanoparticle of 11 hour and 13 hour. We have got this in 100 nanometer scale of more than 1 lakhs. And this is basically the HT and EDS image SPPR tungsten nanoparticle. You have got some fringe pattern at 10 nanometer particle, 5 nanometer particle, 2 nanometer particle, and 1 nanometer particle. And this is EDS image. So this is basically the references of my work. So future scope, we are also doing multi-scale. So prediction through multi-scale modeling and experimental validation is needed. Synthesize the tungsten nanoparticle through chemical route, and then process the targeted nanocomposite through powder metallurgy route. Now, perform different structural characterization of the synthesized tungsten nanoparticle, and multi-scale modeling link up through different techniques like DFT and AFM, etc. And I acknowledge Center of Excellence Grant for Advanced Material and the TCUP 3, Professor M.M. Ghosh, the HOD of department, my PhD supervisor also, Professor K.S. Ghosh, and Professor Anirban Das, Professor Ashish Mitro, my family and friends. So Vande Mataram, thank you. If you have any doubt, you can mail me or you can ask question.
Sir, there are some questions in the chat box. Anirban sir. Yes, Anirban sir is online. Anirban sir.
Hello, Krishnan. It's a nice talk. Nice to hear you. I have one question. Have you considered any defect or any grain boundary effect here?
No. That is defect free. Totally. We have designed in polycrystal material that in that case we are defect is associated. But we can check it after loading. Maybe the localized deformation is taken. So from DX analysis, that is dislocation analysis in OVITO, we can check it whether how much of partial deformation, frankly deformation is occurred in this surface. We can check it using OVITO.
Okay. No, I'm asking while designing the sample, while designing the things, at that time, have you considered any sort of defects?
No.
You have considered single crystal.
Yes, pure, defect free. So that's why the main reason property is getting high.
So better properties you are getting.
Yes. But we are using different grain size. We are also doing programming in our lab using grain boundary for different polycrystal, like 7 grain, 3 grains. But it will take more time, for 25 days, 20 days. For a if grain size is 10, number of grain is 20, then the programming is getting.
Completion time is very high.
Very high, because we have to develop first the polycrystal using atom scale, and that file fetching in lamps, and lamps is doing later on process.
This will take some time. Okay, there are another 2 questions. Dr. Prof asked one: so why Young's modulus value is intensive to the surface effect?
The surface effect, that means Young modulus is too much high and insensitive to the surface effect due to the nanoparticle. The surface to volume ratio is too high, and the material, whatever we are taking, the defect-free material. So that's why we are also deal with that, because why it is insensitive.
And the second question is there any commercial package available?
Yeah, commercially package is also available, but we are using free site of molecular dynamics, that is LAMPS. You can put in Google, that is LAMMPS, and search it, and you got all the code, and the updated version is also available.
Hello, sir. Hello.
Yes.
Hello, I have a question, sir. Before molecular dynamics simulation,
yes,
whether for indentation test, have you put any property? That means, have you given any property? Because indentation, if material property is not given, Poisson's ratio or Young modulus, then it is very difficult to find out the indentation pattern. Actually, if proper. Okay. So what property you have given? That is
only lattice.
I do not know actually. Only lattice parameter.
Lattice parameter, geometry, and the potential. The interatomic potential.
Lattice parameter, sir, it varies from material to material.
Yes. From, because as we know, it is also you can do it using molecular dynamics. Whether the minimum potential, the corresponding edge length is the lattice parameter. So that you can calculate using molecular dynamics also. We have calculated for alloy.
No, I am saying that you are already assigning from that means the lattice parameter what you are giving, that is the energy required to break the bond. That is you are giving already. That means what is that means you are starting from a point that is you are already taking the consideration lattice parameter.
Yes. That value is given from literature, 3.16.
Okay. Thank you, sir.
Excuse me, sir. This is Saikat Chattopadhyay this side from Jaipur. Hello.
Yes, sir.
Okay, sir. It is very nice talk, and I am also interested. Actually, I am also doing some DFT kind of calculation. My basic interest on zinc oxide and titanium dioxide kind of nanoparticles.
Yes, sir.
So normally we use quantum espresso, this kind of free softwares. So I just come to know that the LAMP software you are using for molecular dynamics.
Yes,
is it possible to do some DFT, means DOS calculation or band structure calculation with this?
I don't know actually.
And sir, it will be helpful for me if you kindly give some means website so that I can find some
Yes. Lamps. Only you put in Google that LAMMPS lamps. You got everything. Any command. Also how to develop the mnemonics. How to develop the properties. Everything. All are there. That is very reliable.
Sir, I'll go through the literature and all those things from the internet, and if I feel anything needed, I will contact you through email.
Yes. No problem, sir.
So thank you very much, sir. Thank you very much.
Okay.
So there are no more questions in the chat box.
Yes.
So thank you.
Hello.
Yes, another question is coming.
Yeah.
Yes, you can ask.
Yeah. Initially, you mentioned that tungsten is quite useful in aerospace structures, and I'm from aerospace background. In aerospace, normally we use carbon nanotube, single wall and double wall. So the method is what you mentioned here. Do you think we can apply for carbon nanotubes also, if you make composite out of it?
So before any prediction, sir, we have to check the life cycle assessment. Okay. So we cannot, this is for the targeted application. We can only predict this material property. You can take it, but we cannot say this is for granted for this for aerospace application. We can only giving some good data, some fit data. But for giving me the targeted application, we have to check the life cycle assessment. Okay. So that is very much important. We cannot say in this way because we have developed in lab scale, but in large scale it is difficult. I know.
Okay. Thank you.
Thank you, sir.
So if anybody has any other questions or queries, you can mail sir. Mail ID is provided in the chat box.
Yes.
So thank you, sir, for your speech or whatever you have delivered. It was very much informative for the participants. Now for the participants, I will just announce that the next session will start from 2 p.m. So everybody just join before time, 10 minutes before time. So we will just end the session over here, and we just again join at before 10 minutes or 15 minutes before 2 p.m.